All right, so in this video, we're going to be looking at how to solve loop current problems using linear algebra. Now, the approach that we're going to take here is not the only method that you can use for solving these problems, and you may encounter slightly different linear algebra approaches in depending on which class you're in and the preferences of the instructor. But what we are going to do is we're going to build our solution based on Kirchhoff's law, which is that the voltage is equal to the resistance times the current. So V equals R times I. When we have multiple batteries or currents in resistors in our problem, then each loop current equation is going to depend on the sum of all of our resistors and currents equal to the sum of all of our voltages. So because the signs are somewhat arbitrary, particularly as a matter of historical convention, for this handout, we're going to choose one that may or may not be consistent with what you're learning in your physics class. So for currents passing through a battery, going from the large side to the small side, we're going to designate this as a positive voltage, and going from the small side to the large side, we're going to designate this as negative. Now, the only difference this is going to make when we actually solve the problem is in the sign of your solutions. So if you turn out that you've adopted this convention and it turns out to be inconsistent with your class, then with like the physics department, just flip all the signs of your currents. It's not going to make any difference in terms of the magnitude of your solutions. It's only going to determine the direction of current flow. So we're just going to adopt this convention because in linear algebra, it doesn't matter. But again, if you're doing this for a physics or electronics class, check for the convention that's used in your course. Now, when we design loop current problems, again, in linear algebra, we're thinking of this as a mathematical thing. Mathematics tends to do things counterclockwise. And so we're going to designate our currents going through the loops counterclockwise as seen in this diagram. And so what we're going to do is we're going to start in each of our loops. And then we're going to construct an equation that includes all of the resistances and batteries and voltages through the entire diagram for this one current. And then we're also going to include any other currents that it might be interacting with. So it is possible to do these loop current problems on any sort of combination of loops. So in this case, we have 1, 2, 3, 4 sort of smaller loops, but you could also create a loop current around the exterior or around any place where you can go around in a consistent loop. But that will affect the way that you then at the end add or subtract your currents from each other. So it's just important to kind of keep that in mind. We're going to need, since we have 4 currents to solve, we're going to need to set up 4 equations. But again, there's multiple different kinds of loops that you can construct in any diagram like this. And so just because I've chosen this convention, this is a standard practice in linear algebra, but you just need 4 equations in order to do this. And so you can designate your loops either as I've done in them or in a slightly different configuration, and you'll still get the currents. Again, the only difference is going to be when you're trying to figure out how the currents are flowing through a particular segment of the diagram, then you'll need to add or subtract your currents appropriately based on how you've designated your loops. So this, I find, is the easiest way to set these up. Now, if we're going to begin with I1, which is our first current loop going through this top left corner of our graph. Now, the first thing that we're going to recognize is that according to our convention, we're going from the small side to the large side. So we're going to designate this voltage on this loop as minus 40. And then we're going to continue around our loop. Now we've encountered a 1 ohm resistor. And so we're going to add that to the Ri side, the other side of our equation. Now, this resistor is not interacting with any other currents in our diagram that we're going to be using. So this is just 1 ohm resistor times current I1. And then we continue around our loop. Now we've encountered our 7 ohm resistor, but in this case, we have a I1 current going through the diagram this way. So we'll add the 7 ohm 7I1 to our equation. And then as we continue through the resistor, we're also encountering a 7I2 current going through the other direction. So this resistor is shared by both I1 and I2. And so we're going to have to designate that 7I2 also as interacting with this current to the other side of our equation. So we'll be adding 7I1 and minus 7I2 to that RI side of our equation. Now, if we continue going through the loop, then now we're encountering a 4 ohm resistor, and we're going to treat that the same way that we did with the 7 ohm resistor. We're going to add 4I1 to our RI side of the equation and minus 4I4 to that side of the equation as well. Now, why the sign change? Well, when we're going around our I1 loop this way, our I1 current is going through the diagram from left to right. But if we're going on the I2 current, then the I2 current is actually going through this section of the graph from right to left. So that's that sign change. Same thing for the I4 or the R4 resistor, the 4 ohm resistor. When we go through on the I1 current, we're going from bottom to top. But as we go through as an I4 current, we're going from top to bottom. So that direction is designated as a minus sign to indicate that the flow is in the opposite direction. And once we've added all of these components to our equation, we come back to the voltage where we started. So we're going to get our equation to look like this. So we had the 1 ohm resistor for the I1 current that had no interactions with it. We had the 7I1 and the minus 7I2 from that bottom section of our graph. We have the 4I1 and the minus 4I4 from that right side of our loop, and then that's equal to our negative 40 voltage. And so when we combine like terms, we end up with 12I1 minus 7I2 minus 4I4 is minus 40. Now, we're going to continue setting up our equations for this, all 4 of these loops. So for instance, as we go around our I2 current here, again, this one is shared, this resistor is shared by I2 and I1. So this will be 7I2 minus 7I4. Now we're going through another battery, again, from the small side to the large side. So we designated that as negative. So negative 30 will go on our voltage side of the graph of the equation. Then as we go through our 2 ohm resistor, that is only 2I2 because it's on a section of the loop that has no other currents on it. And then on this one, we'll also add 6I2 minus 6I3. And then we come back to that top side where we started. The I2 coefficient will be 7 plus 6 plus 2, which is 15. And then we'll have, again, minus 7I1 and plus 6I3 equals negative 30 as our equation. Like so. And then if we continue around the I3, then we start at the top again. So this will be 5 ohm resistor, but shared between I3 and I4. So that will be plus 5 I3 minus 5 I4. Here we have the 6 ohm resistor being shared with I3 and I2. So plus 6 I3 and minus 6 I2. Here's our battery. Again, we're going in the negative direction that we adopted. So this will be a negative 20 on the other side of our equation. And then this resistor is only on the I3 current. So that'll be plus 3I3. So if we add up all of our I3 resistors, we end up with 14I3 minus 5I4 minus 6I2 is equal to negative 20. And then, and then finally, and it's a common convention to put them in the order of the 1, 2, 3, 4 subscripts, because we're going to put these in a matrix, and so we should put them in the right order. And then as we go through the I4 current, again, starting at the top, we have our 4 ohm resistor, which is only on I4, so plus 4I4. And then here we have our 4 ohm resistor shared with I4 and I1. So plus 4I4 minus 4I1. Here's our 5 ohm resistor shared with I3. So plus 5I4 minus 5I3. And then here we're going through our battery from the positive to the negative side. So that'll be plus 10, because that's or the sequence, the direction that we designated as positive. So our coefficient of I4 will be 8 plus 5 is 13. And then we'll have a minus I1, a minus 4I1, and minus 5I3 is equal to positive 10. And so we end up with this equation. Now, when we put them all together into a system of equations, we end up, again, we have 4 unknowns, 4 loop currents, I1, 2, 3, and 4, and we have 4 equations, which means that assuming that these are all independent, we should be able to solve for them. It's actually hard to make these so that they can't be solved unless you have too many equations or too few. So the numbers that you're going to get from solving problems like this tend to be appalling. They're not nice fractions. They're just crazy decimals that often the calculator can't even convert back to fractions for you. So we're going to turn this, because this is a linear algebra problem, we're going to turn this into a matrix in augmented form. Now, the only thing to be really careful about here is where you don't have one of the currents in the equation, to make sure you fill it in with a 0. Even though I have only 3 terms in each equation, the coefficients are not all the same in the column. So the first equation becomes 12, negative 7, 0, because there's no I3, minus 4, and then minus 40. And then we have 7 and 15 and minus 6 and 0 I4, and our minus 30. There's no I1 in this equation, so 0, minus 6, 14, minus 5, and minus 20. And then finally, minus 4, there's no I2, minus 5, 13, and 10. Now, again, the thing to keep in mind here is that the easiest way to solve these is in the calculator, using the row reduce echelon form function in your calculator, in your TI. How to do that maybe in another video. But the main thing here is you don't really want to try to solve this by hand, because it is awful. And these problems rarely come out nicely. Now, when you solve this particular example, you should end up with the following currents. And then again, if you want to determine the current in any particular section of the wire, you need to add the currents together with appropriate signs for their directions in that particular section of the wire. So where the I1 and I2 currents are flowing in opposite directions, you would add them together by flipping one of the signs, depending on your convention about the direction of flow.